Okay, I'm just going to talk about some of the neat features. I've covered this in other videos, but I'm just going to, whatever comes to mind. Okay, so I want people to get familiar with, this is the directory structure. There's 20,000 lines in the compiler, 24,000 lines in the kernel. Those are the only two binary files. You never need to make objects or executables or anything. You just run from source just in time. In the demo directory, for example, we can go in and try a game. So we go in Bomber Golf. We have graphics in source. And we hit F5. And this is counting keystrokes to destroy the tank, all 10 tanks. Anyway, so if you hit, it's command line driven, but it feeds into a C compiler. So if you say i64 count, i64n, i64i, for I equal 1, semicolon I less or equal n, semicolon I plus plus, %d, carriage return. This is print. I have my own language. And a string by itself is printf. I can say, if you do a statement outside of a function, it's executed immediately. So, oh, I didn't return a value. Oh, well, it didn't mind. So let's do unassemble function count. It's 64-bit assembly. It's a true compiler, not an interpreter, even though it's just in time. It uses register variables. These RDI is N, RSI is I. And if we say ctrace on, that'll trace the compiler as it's doing statement. So if I say 1 plus 2, that loads a 3 and returns it. If I say count 10, it pushes 10. The call, I have my own calling convention. It uses the return and pop, so that the caller doesn't pop, the function pops the arguments. Anyway, it pushes 10, calls that function. If you want to say who minus r, we have one local variable. I can make a global i64i, I equals 5. It's moving 5 into the global location. This happens to be a RSP relative. I put it in, I have two, all code goes in the lowest 2 gig. You'll notice these addresses probably look strange to you. I think the lowest 2 gig is the code heap. Anyway, so I don't have kernel. If we do a memory map, you can get this on my website. Alphabetic order, numeric order. So this is in numeric order. When it loads in the module, it loads in at 7C, and we have some local variables, and the boot is at the beginning. It's assembly, and so we have this loads into the low 640, and I just leave it there. I identity map, so I have no reason to move it. Then when it starts up, it starts compiling and putting on the code heap. The code heap allocates off the top. It slices off the bottom of a slab, or no, the top of a slab. I'm sorry. And so when it allocates for just in time, it just calls malloc. So some people think it's address randomization. No, it's just malloc. And these are all functions that are in memory. you can use unassemble. I wrote my own compiler, end assembler and unassembler. So that's that. So we can go. We can do mem BIOS rep. This is this is from the BIOS during boot. It boots in real mode, and it calls the BIOS to get some information, and then it switches to 64-bit mode. And since I have identity mapping, my physical memory is the same as my virtual memory. So all of these, I have gaps and stuff. It's fragmented. That's just the way it goes. Anyway, so my operating system can use call relative 32 because I put all code in the lowest 2 gig. All my code is in this chunk right here. Anyway, when it starts up, so I have my own bootloaders and stuff. I have a CD-ROM, hard disk bootloaders. What those do is they're really, really simple. They don't navigate the file system. What I do is when you run I have a professional install script that installs my operating system onto the disk. Anyway, and when it installs, it locates the block address of the if we change to in the root directory is kernel.bin. It locates the block address and it puts it into the bootloader. So the bootloader has a hard-coded patch that has the block address, and it just uses interrupt 1342, and it loads in block by block, one block at a time. I'm conservative. The biggest challenge is compatibility, and you don't want some stupid reason to make it not work because BIOSes are all different. Anyway, then it jumps in real mode to my kernel. It loads in the kernel. It starts at kernel start. I have a run level. I just tick off bits. It's not like Linux. So it starts in 16-bit mode, ticks that off, enables VGA, enables 32-bit mode, long mode. Then all my code is position independent because I patch. I have a ridiculous table that's used to patch the absolute addresses, but it's okay. I switched to 64-bit mode, so I have to self-patch before you can run the code. I have to add the module start to all the absolute addresses. I switched to 64-bit mode. I have a preliminary heap that's not quite the full heap, and then I enable the full heap. I have so the memory has the code memory and the data memory. Anyway, I enable raw black and white output to the console, so there's no console until this bit is flipped. So if you're debugging, don't use the console output until this bit in the boot up process. Then it enables interrupts and enables multi-core. I don't do symmetric multi-core. I do master slave. So all applications run on core 0. And when they want, they just explicitly spawn tasks on other cores. It's a lot better. You can do things like a real-time flight simulator where each task is doing a strip. If you have SMP, it might decide not to schedule, and suddenly you would have a glitch because suddenly instead of 7 slaves doing, instead of 8 cores doing a strip. Let me show you I got sidetracked. Oh well, we're not in any hurry. So instead of when we do so this is updating 30 times a second, but you're only seeing a video of 8 times a second. Believe it or not, I'm writing the frames to disk 8 times a second. And my multi-core is not symmetric because I have a master slave. That if the scheduler decided to bump 2 tasks on 1 core, suddenly it would take twice as long, and you'd have a glitch. So you just don't want the scheduler to touch it. You just want to put it there and keep it simple. So only tasks on core 0 can have windows, and only applications can run from core 0. That's not really enforced, but there's locks on heaps and disks and stuff so that you can do multi-core. Anyway, I enabled the disk code gets started up, and then I load the compiler. That's a separate module. The first module is the kernel. Then I load in the compiler. Those are the only 2 binaries you ever need. Everything else can run just in time, where it just mallocs code and shoves it in there and patches it, and it's ready to go. This is my, it enables the document framework. That's what has the editor, the tree widgets and links and all that. I have a task for the window manager. That's what 30 times a second, no matter what, it redraws the screen. I can show you that. It logs into my account and loads my registry file. The registry file is for high scores. You can delete it, and it defaults to safe values. Just delete the registry, and it'll be, the policy is it's supposed to default to safe values. It's really easy to make high scores in the registry file. So Adam 2, Adam is like Adam and Eve. It's the first task. And all tasks are children of Adam, and it starts in the kernel directory, and then it goes into the Adam directory and compiles. In the kernel directory, it compiles headers. In the Adam directory, it compiles code, and then it goes into a server mode. Adam is this window. Here, this is Adam. You don't directly don't directly type in Adam. He's a server. You tell him to print hello. I just made him print hello. If you want system-wide code, you tell Adam to compile the code and you include with Adam. It feeds into a C compiler, so the way you execute at the command line is you pound include. So for example, when we run a game, let's run Wenceslas. I'll show you. You can right click and do it fast, or you can say, since it feeds into a C compiler, and any statement outside a function executes immediately. So look at this. At the bottom it says Wenceslas. That's a statement to execute the code. I could hit F5, but we're going to do it like this. F5 causes a new task. This is the same task. So anyway, I'm going to execute this. I need a semicolon just because, it's showing, I told it to trace the compiler output, so we're getting, that's kind of weird. I think we have some data or something. Anyway, so in this Good King Wenceslas led the peasants. He had a guy walk in his footprints because it was cold, and so you try and make these people go to a tree for warmth or go inside the house. They follow your footprints, and your footprints disappear. Anyway, so watch here. He's going to go in the house. He went in the house. This guy's warming himself by the fire, so you got to get all 10. So I try to be original. If it's not original, it's not worth doing. Oh, I'm really proud of my new game. My new game is called Chestnut. This is supposed to be like, the idea was armies with computer bandwidth links, and trying to isolate. So each side tries to step on the midpoint of the link, and if you isolate the king, then you win. It's actually I haven't figured out how to play it. It's I can tell it takes it's an intelligent game. Some of it is estimating the midpoint after you do it. That's kind of not fun. Maybe, I don't know, maybe it's fun. The nice thing is it's good for a reversal all the way until the end. If you screw up, you can have a big reversal. Like this guy goes and steps on. If he's walloping the other guy, then there can be a big reversal where he. Anyway, so I'm curious to see what strategies happen. It's an exciting new game. We can test your IQ, see if you can figure out how to play it. Anyway, where were we? So we go in the startup directory, and in kernel start, it calls the BIOS, does some initialization, and then at the end it patches, and then it changes to 32-bit and then to 64-bit mode. I wrote my own assembler, so in linker, there's not a linker. I can mix 32-bit, 64-bit, 16-bit, and so somewhere in here it jumps to kernel main. So this is kernel main is in kend, and this is where it's. I can't use the C compiler at this. I can't use C at the beginning because my C compiler is only 64-bit. I don't use the standard argument passing. I don't use the register. I don't use register arguments for passing into my routines. I use 64-bit has 16 registers. That's actually easier to make a compiler for. Anyway, you can look at the videos on my compiler. So when it initializes, I told you all those initializations. Here's where it loads the compiler module, and then it starts executing code in Atom1. And each task has an environment symbol table I told you about. So these are all the environment. These are all the symbols in the symbol table. You need to stop thinking of scripting as a amateur language. This is optimized C. It's if we unassemble these things, unassemble function. Optimize. Let's look at some code. Oh, let's look at functions. Wenceslas. No, that's too big. What's another one? Song task. Let's look at song task. It's sitting in memory. So it's optimized 64-bit code. This is, even though it just pound included. Remember we pound included Wenceslas. So it's all in memory, and my songs are just a simple one voice. It's a delightful language. Just the note, middle C, octave 3, eighth note C, C. And it's really easy to spawn tasks. So there's no distinction between thread, process, or task. Everything is it's identity mapped. So it's single address map. So honestly, it's kind of like for one video game at a time, and that video game can have multiple threads. It doesn't share the disk. So if I do a long disk operation, it doesn't break it in pieces. So it's not good for a server or something like that. But my vision is a Commodore 64. You don't need to play two video games at once. So I call it one process with multiple threads. That's even though it is multiple processes. But anyway, I don't want to oversell it. So FS is the FS segment register. It just compiled to fetch FS. This is the The FS segment register points to the current task record. This up at the top, you see up here at the top, the 3FD5, all that, that's the current task record. We have a feature called WordStat, which, or not WordStat, it used to be called WordStat. Now it's just autocomplete. So we can click on C task, and it's a, my vision is a Commodore 64, and that was open access. The kids are supposed to have fun. Everybody's supposed to have fun playing around with the code. So we just directly access it. That's the whole point. It's supposed to be fun. Linux is too ugly and complicated. I want everybody to not be intimidated. Press F1 and just go through the list of all the API functions. My dates are 64-bit. It's based on AD0 is 0. So in the upper 32 bits are days since AD0. So you can, and the lower 32 bits are fractions of a day. So you can add and subtract numbers, and at times work. So it's date time. Anyway, so I want you to go through and get familiar with all these. Once you, I don't want it to be intimidating. I want you to see the light at the end of the tunnel. And anyway, so it looks like it's text mode, but check this out. The Apple II used to have a really simple way to draw graphics. And I said, you know, we need to think like we're making a 1040EZ tax form. A 1040EZ tax form is really simple, and it's a big deal if you make it more complicated. You would fire somebody who made an extra box on a 1040EZ tax form. So we want this simple, so that it's painful for, it's just like filling out taxes, an extra box on a tax if you have to do something. So I streamline it, and I keep it purposely simple. Anyway, so if you want to see the right now on the wallpaper is all the tasks that we have. We have there's a Seth task on each core. That's the manager for that core. Adam is the Seth task on core 0. Anyway, we're doing we can do 4 million swaps a second. I update the screen 60 times a second no matter what, 30 times a second no matter what. There's a window manager. The standard tasks that you always have are the Atom task and the window manager, and you'll also have the autocomplete, and then there's just a couple consoles. I try to keep the tasks down to a minimum. So my window manager does some all the miscellaneous stuff the window manager does. You know, technically the window manager window is the wallpaper, and it's ordered according to the Z buffer order. The order in the task queue, it's just a round robin. The order in the task queue is the Windows Z buffer order, so it's really simple. And so we were talking about during boot, it goes in and it starts compiling Atom 1. This is like OtJdYdzUsYU. Basically, during startup, it compiles. It has compiled 50,000 lines. Look down here. There's 50,000 lines of code that have been compiled. That's during boot. That's what we're looking at right here. During boot, it goes through and does all these includes of the header kernel. You have two binary modules, the kernel and the compiler. It includes a header for that. And then it goes into the Atom directory and starts compiling. We have 50,000 lines we compiled during boot. That's the headers. And then the Atom directory is, all this code gets compiled during boot. It starts with Atom 2, and it includes the graphics library, the window manager, the editor, and then when it's done at the bottom, it goes into Atom 3, which is this is your home directory, and then it starts compiling code in your home directory. Now, files, if they're not found, it searches the parent directory. So my home directory, you'll notice there's default files here. If I have there's an Atom 3 localized, that overrides the defaults. If I make my own, you can copy these into your own directory, and then it's overriding it. The file system doesn't have a path. It searches the current directory for a file, and if it's not found, it searches the parent. You can see what the path doesn't make sense because we're feeding into a C compiler. If I say for I equals 0, I less than 10, I plus plus %d, comma I. Oops, that didn't work. I think we had, I don't know what happened. I better control C. I don't want to ruin my video. Anyway, so where was I? So if you go to F1, you get to the help. There's a really big demo index. This is full of all kinds of beginner, advanced. This is how you learn the API. You just work your way through all the games. I've decided that I've fully tested. This is a proven operating system. It works for what it was designed for. I have modest goals, and anyway, it works for what I intended it. Anyway, so let's see. So GS is the CPU, the current CPU core. There's a CPU structure. It has a you do debugging and stuff at the command line. Like I can say dump 10,000, and this dumps. That's a hex dump. If you say doc dump 10,000, this is a variation, and it's a live widget. We have live widgets at the command line. There's class rep. It knows the type of the. We have all the compiler information is retained in memory. We have source debugging. This is kind of like how you debug. So we're going to dump the FS segment register. So this is the record and all the stuff in it. So this is like your IDE. I used to have. Anyway, so the way you develop is you oops, Alt M. So what you do is you use 0 main. Let's do. I could do it even less. Let's say hello main. Then you hit character turn. You use the cursor keys. It's really delightful. And then include. And it said hello there. We can put some character turns in here. So character turn. Hello. Okay. So we have graphics at the source. If you hit Control R, you can make a sprite. Let's do a couple circles. It's vector graphics, but you can convert them to bitmap. We're making a series of vectors over here. Let's do color green, light green circle, and then let's do a dithered light green flood fill, and then let's just call that good. Let's edit it, and there's an origin. There's no bounding box. Shift origin. Okay, so it has an origin. Now we come down here, and we can say I'm just gonna the simplest. You don't normally do this, but Control R is your sprite menu, and we want binary numbers. We have graphics in source code, so I'm gonna kind of cheat here. Let's do this. Now we have graphics on the command line. Now notice the flood fills are done as vectors, so we don't really want that. Let's convert it to bitmap. This is a critical thing. We're convert to bitmap. use transparent background, use these extents, yes, exit. Okay, now it's a bitmap. So the flood fills are, okay, now, anyway, now the flood fill does not interact with the under, if you notice here, the flood fill interacted with the underneath. Now the flood fill doesn't interact. Anyway, so that's my introduction.